The topic for this video is U substitutions, section 5.5. As with any of the antiderivatives that we've been doing lately, or indefinite integrals, however you want to think of them, U substitutions are going to be looking for ways to undo a derivative. And in particular, the U substitutions are precisely working the chain rule backwards. So I'm going to start by looking at the chain rule for derivatives and see what it does, and then see what I can do to work it backwards. So I'm just going to, take a problem from Calc 2 here. So recall, suppose I had the derivative of something like the sine of x squared dx. Right? To take derivatives of this sort, we say there's an outside function and there's an inside function. This is the sine of x squared. So the x squared's on the inside, and it's the sine of that. To take the derivative of such a thing, we're taking the derivative of the outside function, leaving the inside alone. So this is the cosine of x squared. But then I need to multiply by the derivative of what's inside. So then I multiply by that 2x, which I would generally not write that way. I would put the 2x out in front, but multiplication is commutative, so it doesn't matter if you put it there or out in front. However, it's not uncommon for people to write cosines without parentheses, and so you'd have the cosine of x squared times 2x, and the 2x and the x squared might get together if they're written that way. So I don't like it written that way, because this is inside the cosine and this is outside afterwards. So anyway, the point is, the chain rule pops out this extra 2x here, which is the derivative of the inside. Now, another way we write that is like this: d sine u dx is equal to the cosine of u times du dx. Now, if I say that u is equal to x squared, then du dx is 2x, and we end up in the same place, right? There's the cosine of u, but the cosine of u is x, well, u is x squared, and then du dx is that 2x. And again, we end up in the same place, right? But the thing I see coming out of the chain rule is that inside the parentheses is this thing we called u, and outside the parentheses here, this thing on the end, is what ended up being the derivative of u, right? Now that's written in derivative notation. If we write it in differential notation, it might look like this: d of sine x squared is equal to cosine of x squared times 2x dx. Okay. Or on the shorter version here, the derivative of the differential of sine u is the cosine of u times du. Okay. In fact, if you just take this equation right here and multiply both sides by dx, that's what this one is. And if you take this equation up on the top here, multiply both sides by dx, that's what that one is. So anyway, these are differential equations. These are derivatives equations. The point being, the chain rule pops something out. You take the derivative of the outside function, and then you multiply by the derivative of the inside. In order to go backwards, we've got to recognize what's that thing that got popped out, what's that derivative of the inside that gets thrown in there by the chain rule, and then we're going to take it away when we do an antiderivative. Okay. So let's do an example here. For instance, actually this example, suppose I want to work this backwards. Suppose I wanted to do the integral of 2x times the cosine of x squared dx. Right? Now granted, I just did it up here that I know the derivative of this thing is that, so the antiderivative should get me back to here. But let's see how we work that without having just seen it happen. Now a U substitution is something that you can try at any time. At any time you're trying to do an integral or an antiderivative, however you think of it. You say, well, let me try a U substitution and see if that helps me. It might not. I'm going to do it like this. I'm going to say let U equal Now thinking in terms of here, u is always the thing on the inside of the parentheses. So if I've got a problem like this with stuff inside of a function and stuff outside of the function, my kind of first thought is to make the stuff inside be the u. So let u equal x squared. Now there's something else I have in mind too, but I'll say that as we come up. If I let u equal x squared, then what's du? Well, du is the derivative of that, 2x times then dx. Okay. And that's the thing, the other thing that I have in mind is that not only am I looking for something inside the parentheses, I'm looking to see that its derivative is somewhere outside the parentheses. So there's a 2x sitting out here. Okay. So looking at this, inside the parentheses here is the u. Outside the parentheses, the 2x dx is this thing right here, and that's du. So this integral looks to me like it's just cosine of u du. Right? The x squared here gets replaced by the u, and the whole 2x dx, all of that, 2x dx, all got replaced by this simpler thing, just cosine u. Essentially, we went from this equation here to that one by replacing the x squared by u, and that forces the 2x dx to be replaced by the du. Okay. This now is just a simple antiderivative. We can do the antiderivative of the cosine of u as the sine of u plus a constant. Don't forget your plus a constant because there's lots of antiderivatives, just different plus c's. And now we can substitute back in where u is equal to x squared. And so we have the antiderivative of 2x cosine x squared dx is sine x squared plus a constant. All right, the integral of that is this. Let's try another example. How about, what's my next example? How about something like, oh yeah, something polynomial. Sorry, I'm trying to flip the page here and it doesn't want to flip. There we go. The integral of x cubed times 3x to the fourth plus 7 to the 9th power dx. Now this is a problem that I could do without u substitutions because this is just a polynomial raised to a big power. I could multiply this whole thing out. You know, 3x to the fourth plus 7 times 3x to the fourth plus 7 times 3x to the fourth plus 7, 9 times, big old foil, multiply the whole thing out, distribute the x cubed into that whole thing. And it has to have this, what would that be, 31st degree polynomial? It would be big. But we could take the antiderivative because polynomials are easy to do antiderivatives of. However, this is really not a good way to do this problem. But I do see stuff inside the parentheses. So I'm inclined to think, hey, let's let u equal 3x to the fourth plus 7. What's du? Well, it's the derivative of that times dx, so the derivative would be 12x cubed times dx. Well, I don't have a 12x cubed, but I have an x cubed dx. So I think like this. Actually, there's a couple ways I think of this. In fact, I'm going to do this problem and the next problem slightly differently, but they're equivalent. You can pick which way you like. I see an x cubed dx, so I got an x cubed dx here. X cubed, times dx is equal to du divided by 12. So just take that 12 and divide it there. And so the x cubed dx is all going to turn into just a du. Right? Then inside the parentheses here is the u, but that stuff is being raised to the 9th power. So this is something to the 9th power times the derivative of what's inside. Sorry, the du is du divided by 12. Sorry, the x cubed dx is du divided by 12. I did all that calculation and I neglected to put the divided by 12 in there. But here it is. So, but now the 1 over 12 is just a constant, and that can come out in front. One of the properties of integrals is that the integral of a constant times a function is the constant times the integral of the function. So this is just a du to the 9th du, and now this is just a nice polynomial. All right, this is a u to a power. I can integrate that. That's 1/12 u to the 10th power divided by 10 plus a constant. That constant isn't necessarily 0, plus a constant. And now I'm going to go back. What was my u? u was 3x to the fourth plus 7. So I've got 1 over 120 times 3x to the fourth plus 7 to the 10th power plus a constant. Okay. So I didn't quite have the du there, but all I was missing was multiplying by a constant. And that's just okay, because I can just divide by that constant and get it over there. Right? One thing to remember when you're doing these u substitutions, that when you get done, when you get it switched into u's instead of x's, there can't be a mixture. There can't be x's and u's. If you've still got x's in there, then you got to keep working, or you got to do a different u substitution. It's got to turn all into u's. No mixtures of variables. Not at this stage of the game. When we get to Calc 3, we'll be able to handle a couple of variables inside of an integral, but not yet. So anyway, there was that one. Let's try another similar one here. Next example. How about the integral of x times the square root of x squared plus 1 dx? Okay. This one looks a little different because it's not so obvious of parentheses, but you do have stuff inside of another function. You've got all this x squared plus 1 inside of that square root function. So let's let u equal the stuff inside x squared plus 1. What's du? Well, du is the derivative times dx. Now, in the previous example, I said, well, look, I don't have the 2x dx, I just have an x dx, so I would have divided by 2. Another way that, actually this is the way I was taught originally, you can do it this way if you like or not. I look at this and say, hey, I really like a 2x dx, so let me throw a 2 in there. So now I have it. But I can't just go multiplying by 2 wherever I want. I've got to somehow compensate so that I don't change the value. Well, I can multiply by 2, and I can also divide by 2 in the form of multiplying by a half out in front. So I throw a 2 in, I take a half out, that cancels out. That's the same as multiplying by 1. But what I've done is now the 2x dx is right there. That's my du. So there's a half out in front. The 2x dx turns into the du, and what I'm left with is a square root of u. Right? The x squared plus 1 was that inside, and that's all under the square root, so square root of u. And this is an integral I can do. I seem to be at a page break here. I'm going to write this as 1/2 the integral of u to the 1/2 du. So that's, again, just like a polynomial. It's like a power rule here. So it's going to be u to the, sorry, I don't know why. It's going to be u to the, add 1 to that. Be careful. You're not taking the derivative where you subtract 1. You're taking the antiderivative where you're going to add 1. So if I add 1 to 1/2, that's now, come on now, that's 3/2. And then I'm going to divide by 3/2, and I still got the times 1/2 out in front here, plus c. Okay. Dividing by 3/2 is the same thing as multiplying by 2/3. In fact, I generally don't write this step down when I'm doing it myself, just because I know, hey, I'm dividing by a fraction, I'm just going to multiply by the reciprocal. So anyway, u to the 3/2 plus c. The 2's cancel out, and I've got 1/3. U, remember, do we remember? What was u? Way back up here, u was equal to x squared plus 1. So this would be x squared plus 1 to the 3/2 power plus c. Right? You got that 1/3 out in front. You can double check this by taking a derivative. Notice if I take the derivative of this thing, the 1/3 comes along for the ride. The 3/2 would be multiplied out in front. The 3's would cancel out, leaving just a 1/2. And then you'd have this thing raised to the 1 less power. Well, if you take 3/2 and subtract 1, you got the 1/2. But then the chain rule says multiply by the derivative of the inside, which gives you an extra 2x. Well, the 2 and the half are going to cancel out, leaving just an x, and I think we get back to where we started from. Right? I didn't write anything down there, I just said it, but taking the derivative does get you back to the function we started with. Okay. So there's the basics of u substitution. I'll do some more complicated ones in my next video.